Okay, now we're on page 3 in the Chem 120 Unit 2 note packet. We're going to talk about electron configurations and the periodic table. The periodic table contains so much information. It gives chemists the ability to explain known chemical behavior of elements and predict new ones. I just have a very basic periodic table here. It's kind of nice because it's simple. The periodic table that you will get to use when you take exams looks like this. So it's definitely more complicated, but you need it to be more complicated because you're going to learn how to use all the different things on this periodic table. Well, I take that back. Maybe not everything, but a lot of information on this periodic table. When you first look at the periodic table, it's like, oh my gosh, there's no way I'm going to be able to learn this and how to use it. I'm just going to drop this class. There's no way I can get through this class. It's going to be, I can remember being a student and thinking that, oh, this one class is just going to kill me. I'm not going to be able to get my degree, which I'm not going to be able to get a job. I'm going to be a bum, and I'm going to live on the river. You know how sometimes this anxiety ramps up, especially if you've had lots of caffeine. So you will be able to learn how to use this periodic table. And granted, these periodic tables contain a lot of extra information that we don't use, but they are kind of the nicest periodic tables that we come across to use for students when testing. Now, I've had students say that they had to memorize the periodic table. You will never have to memorize the periodic table in this class. We will always provide it to you. There are things that you can do to help you better utilize the periodic table so that you're using it more efficiently. If you know some of the symbols and where they are, it can definitely be helpful. Like carbon is used a lot, nitrogen is used, oxygen. So knowing just roughly where they are in the periodic table can be very helpful. Knowing abbreviations for elements can help too, but this periodic table, I'm going to zoom in here. Like Fe, you wouldn't necessarily think of Fe as being iron, but that is the abbreviation for iron. But this periodic table has the name written underneath it, which not all periodic tables do. So we wanted you to have that. It turns out that iron got its name way back when the elements were named in Latin or Greek. So it's actually ferrum, and that's where you get Fe, and so that kind of makes more sense instead of iron, I-R-O. There is R in an element, I-R, no, maybe, yeah, iridium right there. So, but anyways, we don't want you to memorize periodic table, you don't have to do that. So, but this is what the one that you're going to be using at the testing services will look like. Now back to the simpler one. We'll start here, and then we'll kind of get a little bit more advanced. The periodic table is kind of grouped into metals and non-metals. And so the metals are on the left side of the periodic table, left side, and middle. They're in this light purple. Probably when you printed yours off, unless you printed off on a color printer, you didn't get this nice color. But the metals are this lavender. These are transition metals in here. Like this. Transition metals. And there are more metals here. Now notice that this little element right up here, this one happens to be hydrogen, is not a metal. So that's important to distinguish. But metals, they're unique. They can conduct electricity. Some properties about them. They're malleable. And they display ductility. So they can be drawn out into wires. Now, nonmetals, they're They're on the right side. Non-conductors. I should also mention that metals conduct heat, so electricity and heat. Non-metals are non-conductors of electricity and heat. So it's important to point out here that hydrogen is a non-metal as well. Now, other examples of nonmetals would be oxygen, fluorine, chlorine, neon, argon. We'll talk about them more coming up in this lecture. Now, metalloids, another name for them is the semi-metals. So what happens here is they're kind of in between. They're kind of metals, they're kind of non-metals. So they have in-between characteristics. Another name for these, I do need another name to remember, is semiconductors. So semiconductors, we've heard of that, right? Especially with all the technology that we all enjoy, or not enjoy, to take on technology, but certainly benefits of some technology. You hear of the Silicon Valley a lot. So silicon is Si as a semiconductor. Depending on the textbook you use, and depending on whose definition of metalloid, semi-metal, semiconductor that you're using, some elements get put into it, others don't. For our purposes, these ones in green that I have listed here. So usually it's the stair step to the, and on this periodic table, like boron, silicon, germanium, arsenic, antimony, tellurium. And some include polonium, some don't. So I'll put this here. Boron, Si, Ge, As, antimony, Sb, Te, and this one, I would never ask you a test question involving that one because it's not clear. Like the book says, there's a lack of agreement on just which elements fit into this category. Okay. So we've learned the big groups of groupings of what's on the periodic table. We can learn in more detail. So kind of stepping back even further than metals and non-metals and metalloids, just a general thing. Groups are vertical, while periods are horizontal. On the next page, I have this illustration. Periods go horizontal. So this is period 1, 2, 3, 4, 5, 6, 7. And your groups and your families are vertical. And your book has the numbering that I like. I like it. If you look at the periodic table in your textbook, the numbering that really makes the most sense for the groups 1A, 2A, and then if you notice these, it goes 3B, 4B, 5B, 6B. Those are the transition metals. And it goes up to 3A, 4A, 5A, 6A, 7A, 8A. So those are your groups. So I love to have the numbering like this. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. And then the transition metals, which are this darker purple, B, 4B, 5B, 6B, 7B, 9B, 10B, 11B, 12B. Okay, so we're going to learn some specific names of groups or families. Now you think about your family, your last name. You are maybe the Clark family or the Martin family, or wherever your family history is, whatever your last name is, that's your name. And so on the periodic table, we have that too. There are the alkaline earth metals, and alkaline earth metals are group 1A. So any element in that group, they're similar, just like you're similar to your relatives, right? Maybe you have that characteristic, your eyes are a certain color, or your hair is a certain color, so you have, maybe you belong to the alkaline earth metals. So elements in group 1A display similar characteristics, and that's how they got the name, the alkaline earth metals. So like lithium, sodium, potassium, they all display these similar characteristics. That's the alkaline earth metals, group 1A. Okay, so I'll put that here. Alkaline earth metals. Halogens. Halogens are in group 7A. So that's all the way over here. Noble gases are group 8A. Alkali metals. Careful, don't confuse these with alkaline earth metals. That's group 2A. So, alkali metals. Okay, main group elements have the number, or have the letter, have the letter A after the name. A. Okay, transition metals have B after, sorry. Okay, intertransition metals, I don't really have this on this pretty periodic table, on a simplified one. But these over here are your intertransition metals. So they're, a lot of times, chemistry textbooks will refer to this as an island of instability. Maybe sometimes you feel like you belong on an island of instability, like you're just having an off day. But the reason they call this the island of instability is a lot of these elements in the intertransition metals are unstable. They're radioactive, they decay. You know, if you generate this element, it's not going to stay that element for long. And this is why we hear about in the news every once in a while, a new element has been discovered. And it only lasted for, a few microseconds because it decays to get to a more stable configuration. And maybe some of you are familiar with radiopharmaceuticals. These are pharmaceutical, these are drugs that patients need, and they're not stable. That's why they're radioactive. And we talked about this in Unit 1. And so a lot of times, radiopharmacists have to work on site. They have to work at the hospital because if you ordered a particular drug that was radioactive and you ordered it by UPS and you ordered it, even if you ordered it overnight, by the time it got shipped to you, it's not going to be that original element or whatever this radioactive element in this compound. So the intertransition metals, a lot of times, are unstable. So that's why that island of instability. So I'll put island instability. Oops. Sorry about this. Okay, so the island of instability. So it's off to the lower right. All right, so I have these instructions. I should have gone on to page 5. Label the families, groups, periods, and sections we just learned on the blank periodic table below. It's good practice for you. So I want you to label the transition metals, the non-metals, the intertransition metals. Where are those? So if you want to, hit pause and then fill these in. And hopefully you got some of them correct. Okay, so we have group 1A, group 2A. Group 1A is alkaline earth metals. Group 2A is alkali metals. Then you have here 3B, 12B, transition metals. Over here you have 3A, 4A, 5A, 6A, 7A, 8A. Group 7A is halogens. Group 8A is noble gases. Over here we have the inner transition metals. All right, so you have your blue. Blue is metals. You have your green. Semi-metals. And then you have your yellow. Okay. So hopefully, this periodic table doesn't look as intimidating. If I asked you on the test, give an example of an alkaline earth metal. You could say, oh, any in this group, so that would be sodium, potassium, rubidium, any of those. And so on and so forth. I could give you a true-false question, true or false, fluorine is a noble gas. That would be false, because fluorine is a halogen, so be careful with those. Okay. Now, on to page 6, the arrangement of the periodic table. There have been several attempts to organize the periodic table. The most successful arrangement was made by a Russian chemist by the name of Dmitry Mendeleev. Mendelev's periodic table was based on atomic masses. Atomic masses. And when he roughly organized the periodic table by atomic masses, he found those group behaviors, like we were just talking about, the alkaline earth metals, the alkaline metals, they all kind of react in a similar fashion. And so he achieved this by arranging them by their atomic masses. And so the one really interesting thing about Mendeleev was that if he found that there wasn't an element where he would expect one, he left it blank and said, this could be an undiscovered element. Mendeleev's periodic table, he left gaps and boldly predicted that these were undiscovered elements. So, it's pretty neat. The modern periodic table, let's see, the modern periodic table contains 114 confirmed elements. This one has 116. So a lot of times somebody will say, I've generated this element, I found a new element, and then it might not exist long enough to see. So at this point, 114 are confirmed. And each element is represented by a box in the periodic table. All right. So, stable electron configurations. I always like explaining this. If you remember from Sesame Street, 8 is great. It truly is in chemistry. When you have 8 valence electrons, you have a very stable element. So, valence electrons, what are they? Valence electrons are the outermost shell electrons in an element. So let's look at carbon. In shell 1, carbon has 2 electrons. In shell 2, carbon has 1, 2, 3, 4. So the number of valence electrons in carbon is 4. So carbon has 4 valence electrons. Okay, so the octet rule states that atoms will gain, lose, or share electrons in order to achieve an octet. There are a few exceptions to this. Hydrogen is a minimalist, just what's one. And then boron is another one. Just 6 electrons. Okay. So when an atom loses or gains electrons to get 8, it's no longer neutral. It has a charge. So an ion is a charged species. A cation is positively charged ion. An anion is a negatively charged ion. I'll give you an example. An example of a cation, magnesium, 2+. An anion, oxide ion, O, 2-. So we're going to learn how to represent atoms using Lewis symbols or electron dot structures. And these just depict the valence electrons. So if you draw the electrons, draw the electron dot structures for the following atoms. Sodium. So if you look at sodium, find sodium. Sodium's in group 1 of the periodic table. So whatever group they're in is pretty much how many valence electrons they have. So sodium's group 1A, it has 1 valence electron. So the electron dot symbol or Lewis symbol for sodium would just look like that. You could have your dot on the top, bottom, or left. It doesn't have to be in the exact same place that mine is. It just has to have 1 dot. Okay, magnesium is in group 2A, so it has 2 valence electrons. So magnesium's dot structure will look like this. Now, when you're drawing Lewis symbols, you want to leave them unpaired as long as possible. Unpaired as long as possible. So, like with magnesium, I didn't put them immediately adjacent to each other. All right. Aluminum is in group 3A, so it's going to have 3 electrons, so it will look like this. Neon, sorry, that's not neon, that's nitrogen. Nitrogen is in group 5. So it has 5 electrons. So I'm going to do it like this. 1, 2, 3, 4. So nitrogen has 3 unpaired electrons and 2 paired electrons. Oxygen is in group 6A, so it has 6 electrons. And if I'm going too fast on any of these, you can always hit pause and kind of convince yourself of this. It's a lot easier for me to go fast when nobody's asking me questions. But oxygen has 6 electrons. Let's go through this. Leave them unpaired as long as possible. So I have 4, 5, 6. Now your oxygen, you could have your 2 paired on the top and the bottom and your 2 unpaired on the left and the right. It doesn't matter, just as long as you have 2 paired electrons and 2 unpaired electrons. All right, bromine has 7 valence electrons. It's in group 7A. So it's going to have 1, 2, 3, 4, 5, 6, 7. It will have 3 paired electrons and 1 unpaired electron. Now neon is in group 8A. It's a noble gas, and it has 8 electrons. Another name for the noble gases is the inert gases. Inert means that they don't react. The reason they don't react is because they have 8 electrons. Remember, 8 is great. They're happy, they're content, they don't need to bond, they're just stable. Okay? So neon looks like this. There you go. Now I have a few questions about these Lewis symbols. Which atom above would gain electrons to achieve an octet? So for sodium, in order for it to have 8 electrons, it would have to gain 7 electrons. That's a heck of a lot of electrons to gain. It's probably more likely that sodium would lose electrons to get an octet. It'll go backwards. So in looking at your periodic table, you look at nitrogen, it's kind of close to a noble gas. So nitrogen would just have to gain 1, 2, 3 electrons to get a noble gas configuration. Oxygen would just have to gain 1, 2 to get a noble gas. Fluorine would just have to gain 1 to get a noble gas. So the atoms above that would just gain electrons to achieve an octet: nitrogen, oxygen, and bromine. Which atoms would lose electrons in order to achieve an octet? These would be the ones that don't have very many valence electrons to begin with. So looking here on the periodic table, sodium. It's quicker for sodium, let me zoom out a little bit. It's quicker for sodium just to lose 1 electron and go to neon. It's quicker for magnesium to lose 2 electrons and then it would have the same configuration as neon. And then aluminum would just lose 1, 2, 3 to get to neon. So the atoms that don't have very many electrons, it's easier for them to just lose electrons. So sodium, magnesium, or aluminum. Now, which atom would neither gain nor lose electrons? That's neon. Neon's happy, content, 8, doesn't need to gain or lose electrons. So on your periodic table, it turns out that the charges, and we'll talk a little bit more about this in the next upcoming lecture, but just to get your idea, get you thinking in this direction. When sodium forms an ion, it loses an electron. So electrons are negatively charged. So it loses an electron. So it's not going to have as much negative charge. It's going to have more positive charge. It's going to have a +1 charge. So you can write that here. Magnesium is going to lose 2 electrons. So it's going to have +2 charge. So anything in group 1 or group 2, when it forms an ion, in group 1 it will be a +1 ion. In group 2 it will be a +2 ion. All right, over here to group 3, aluminum. It's going to lose 3 electrons. So it's going to have a +3 charge. Now carbon, group 4, they don't like to lose or gain electrons. They like to share. We'll talk about those a little bit later on in Unit 4, or Unit 2. Group 5, they gain electrons. They have to gain 1, 2, 3. The electrons are negatively charged, so it's going to be -3. Group 6 has to gain 2 electrons. 1, 2, so it's going to be -2. And group 7, they have to gain 1 electron, so it's going to be -1. And then your noble gases are not going to have a charge. So these charges, if they didn't really make sense to you at this point, don't fret over it. We will talk more about this when we talk about writing formulas and compounds and names from formulas and all that good stuff. So this concludes our lecture for this portion. And, oh, you know what? One more thing. I lied. Transition metals, the ions that transition metals form are in transition. So like iron could be either +2 or +3. Nickel could be +2 or +3. We'll talk about this a little bit later too. But they don't have predictable charges like the main group, the group A elements do. So, okay, work on your homework, and until next time.